Thanks for downloading a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online. Now stay tuned for your 3CR podcast. Hello and welcome to another episode of Lost in Science. We're so glad you're here to join us for another half an hour of the best science you're going to hear in your ears this week. I am Lyndon and I'm joined today by Chris. G'day Chris, how are you going?
I am good, thanks Lyndon. How are you?
I'm very happy to be here, to be talking to you, to be getting lost. I'm very ready to get lost in science today. I really just want to lose myself in the moment in the science. What do you got for us this week?
Well, I don't know if it helps. I'm doing one of the things where I'm trying to get back from being a bit too lost, because it's one of those stories that's very easy to get lost in. It's I saw this in the news the other day, and it was one of those things with an exaggerated headline. In terms of something I thought was quite interesting, but the headline was quite exaggerated. It was on the ABC News website. ABC, the national broadcaster. I don't think I need to explain what ABC is, do I?
No, that's an acronym, surely, that most people can get around.
Yeah. Anyway, the headline was, Atom Smasher spots new clue to explain why the universe exists.
Ooh, that is a good headline. Atom Smasher. I like that.
That is great. It's also the clue to explain why the universe exists. That's what got me.
Oh, well, yeah. Fair.
Yeah, But that was a bit of exaggeration, shall we say. But look, it's still an interesting story, and I'm going to talk about what that means. It's all about the headline implies it's about the reason that there's more matter than antimatter in the universe. It's kind of trying to answer that question, but not really. It's about a puzzle that's been addressed in particle physics, and they've got some new data coming out of the Large Hadron Collider in Switzerland, and I'm going to attempt to explain what any of this means.
Oh, I need some explaining when it comes to that kind of stuff. It's easy for me to get lost. So I'm glad that you're mapping a path for us, maybe with some atomic breadcrumbs or some such. Well, I am going to bring us back down to Earth, I think. Then after that, I wanted to talk about clouds. Clouds are beautiful. They're magical. They're powerful.
Powerful?
Absolutely.
Yeah. They just look so light and fluffy and...
Yeah, some of them are, but a lot of them can pack a big punch. You don't get a big thunderstorm without a big cloud. And it turns out you also don't get the warming that we've had globally over the past few years without taking clouds into account. Yeah, a study came out just a few months ago, or maybe even a few weeks ago, looking at the role of clouds and changes in clouds and what that means in terms of how our global temperatures have changed in the last few years, because temperatures have changed faster than even climate scientists were expecting, and nobody could really explain why. And this new paper has suggested that clouds are to blame. So you think they're innocuous, but actually they've got a lot of explaining to do. And I wanted to listen to them. I wanted to do some of that explaining today.
Excellent. Well, it sounds like we're both going to be explaining things that people didn't think they needed to know, needed explaining.
Yeah, that's true. But maybe not. We'll just have a chat. Let's have a chat about some stuff. Yeah, don't go anywhere.
Okay, yes, you are listening to Lost in Science. My name is Chris, and I am talking about this latest data, this latest experimental results coming out of the Large Hadron Collider in Switzerland that is attempting to give us some clue of why there is something rather than nothing in our universe. There's a lot to unpack there, isn't there, Linda?
Yes. The words seem short, but I know that that's deceptive.
Oh, yeah. Totally.
Yep.
Yeah, look, and there's something that I'm always excited when particle physics makes headlines, because, I am a particle physicist myself, more on the theoretical side, the quantum field theory side of things. And this particular bit of it is not my strong suit, but I mean, let's not get too picky about these things, because it's still particle physics, and technically it is my field, so I shouldn't be complaining too much.
Well, sometimes if it's too much your strong suit, then that can be tricky. You know, people who
Yeah, yeah.
explain something that's their absolute area of expertise, it's very easy to assume that everybody else knows all the words that you do, and then before you know it, nobody understands what you're talking about. So I'm happy to be on the fringes of your knowledge
Okay,
if you'll be able
okay.
to take me through it.
Okay, so briefly, what this is about, it's about a couple of things. One is this puzzle of why there is more matter than antimatter in the universe. Okay, so you think about the Big Bang, this huge explosion of something out of nothing. If it's coming out of nothing, you'd expect it to create equal amounts of matter and antimatter because they're kind of the opposite, aren't they?
Yeah, yep, that makes sense.
And this is something that we expect to see, with fundamental physics too. We like the idea that there's this symmetry at the heart of it, that everything is ordered. And so, yeah, it makes sense that out of nothing you get this kind of equal opposite cancelling out. But of course we don't see that. We see a universe around us made out of matter, and we don't see much antimatter out in the wild. And so this is one of the big puzzles of physics that is to explain, which is, what causes lack of symmetry? Why is matter favored over antimatter? And looking for, is there something in the fundamental interactions that is unbalanced, I suppose you could say, or non-symmetric?
Yep.
Turns out there is something. It was discovered in the 60s initially, and there was a Nobel Prize awarded for it, I think, in 1980. And basically, in one of the nuclear forces, there is a slight difference between how certain particles and certain antiparticles behave.
Okay.
Again, we don't have a lot of time. I don't have a blackboard here. I can't go into too much detail. But so let's a brief recap of what the universe is made out of that we know so far. Okay. So you have atoms that are made out of protons and neutrons in the nucleus and electrons orbiting around them.
Yep, got that.
Okay. The protons and neutrons themselves are made out of tinier things called quarks.
That's the yogurt you can get in Scandinavia. Is that right?
Type of cheese, I think.
Oh, yep. Good.
Yeah.
Okay.
The pronunciation is still, it's up for grabs, whether it's quark or quark. Most people say quark, but the person who invented them said quark. I think the cheese is called quark. So you take your pick. It doesn't really, It's not really important. The point is that they are smaller. They only exist inside the nuclei. And they come in 6 different flavors, we call them. There's up and down quarks. They're the smallest ones, and they kind of make up the most of the matter. That's the protons and neutrons themselves. But then at slightly higher energies, you get charmed and strange quarks. And then at even higher levels, you get either called top and bottom or truth and beauty, depending on which camp you're in. But the T and B is still the abbreviation for them.
Truth and beauty. This is starting to sound a bit like a Twilight novel now.
Well, I mean, some of the names, like the strange, basically quark came about because it came from a particle that was strange. And so people said, oh, that's a strange particle. And so they called it the strange quark. And then when they found another one that was connected to it, I think they've tried to walk that back a bit and they call it the charmed quark. So I don't know. It's all people, as you said, they're small words. They're making up stuff. They're giving them whimsical names. Who cares?
Yeah, the quarks certainly don't care. They're just doing their thing.
So all these particles there are 4 fundamental forces that they interact with. The quarks themselves are held together inside nuclei by the strong nuclear force. They decay and they interact with things like electrons and neutrinos through the weak nuclear force. And then, of course, there is the electromagnetic force, which you'd be familiar with. That's all, electricity and magnetism. And then there is gravity, which is very weak at this level, so we don't worry about it too much. And the weak nuclear force is the one that is the point of interest here, because that's the one that seems to have this kind of slight difference between the particles and the antiparticles. There were certain interactions discovered, like I said, in the 60s that showed that they behave slightly different, and then it was further verified through studies throughout the following decades. But had never been identified with these type of particles called baryons, which are things like protons and neutrons. They're kind of the sort of particles that make up matter. and it never been identified whether they actually are different in terms of this difference between particles and antiparticles. And that is what has been recently found at the Large Hadron Collider, is that they have this, as you know, it's this big machine that whizzes protons, basically, which are your large hadrons, around and around in a circle at very high speeds, close to the speed of light, smash them into each other, and that's with all that energy, you get new things created. And this particular experiment was looking for particles with these beauty quarks in them, these beauty or bottom quarks. And so it's called the LHCb experiment because the B is the beauty quarks. And what they looked at like recently is these baryons. They're called. Stop me if any of this is not making sense.
I think I'm there. I'm holding on by a thread, I believe.
So I should explain that baryons, they're not fundamental particles. They're made out of 3 quarks.
Oh, okay.
So they're not. So the quarks are the basic ones.
Yep.
Baryons are made out of 3 quarks. There's another type of particle called mesons, which are made out of 2 quarks, but baryons are made out of 3 quarks. So a proton is made out of, I think, 2 ups and a down quark, whereas a neutron is made out of 2 downs and an up, if I think I've got that right. Yeah, so baryons are made out of 3 quarks. And so they made these ones called a lambda baryon, and this one's had a B quark in them, a bottom quark or a beauty quark in them, and they observed how they decayed. And they found that, again, the anti-Bs and the positive Bs behave differently, and there was this asymmetry between the way they activate, which shows you there is that antimatter and matter in the universe, in the what we call the standard model of physics, which is the thing I've just described, with all this mess of forces and particles. That itself is not symmetric between matter and antimatter. So it's quite an important thing.
What does that mean next? Yes, amazing, but I'm instantly going to say, okay, well, what do you do next? What's the next experiment?
Well, the trouble is that what it's done is it's verified this basic standard prediction. Unfortunately, the amount of asymmetry they found is not enough to create the matter and antimatter imbalance that we see in the universe, as far as we know.
Oh, okay. So what does that mean? That it's kind of partially answered the question, or they think that once you scale that reaction up, then the imbalance becomes greater? What's their theory there?
Well, so there's a few theories about what could actually be going on. So this is basically just verifying what we already knew, but it's the standard model is the theory that describes all the way these things interact. It is just kind of a cobbled together thing with various ideas that worked. No one likes it because it's not pretty. It's not pretty. It's not simple, and so everyone kind of tends to think there's got to be a simpler theory underlying it all. So it's always kind of disappointing when something agrees with the standard model, because it's like we wanted something that didn't agree, that gives a hint of some new physics. But this one does agree with it. You find the same kind of asymmetry that you have in the standard model. So what you need is something that's a bit beyond that. There's some hope that things like electrons and neutrinos may also have this asymmetry between matter and antimatter. And if that's the case, that may be enough to swing the dial the other direction, but it's much harder to do experiments with those. Like there's neutrinos in particular, it's seen that they can change between different types of neutrinos. I won't go into what neutrinos are. They're very light particles that are related to electrons, but they're so light that they're really hard to do experiments on. And so we don't have any data about whether they have this same property or not. So we can't answer that question. Tend to be, though, that I guess because we think that the standard model is not the ultimate theory, that there is some other theory that potentially would supersede it, that would have a better answer in it, that would have, say, different particles that are ones we haven't seen in our particle colliders yet, that may maybe things that make up dark matter, for instance, but we just haven't discovered them yet. So I think that's the hope that most people lay out for. The fact that these things haven't been seen in any of our particle accelerators is leading some people to wonder, do they actually exist? Do these more fundamental theories actually exist? Should we just settle with the standard model? But the fact that we have a universe of matter shows that there is something going on, so there is more to be discovered. So yeah, we know it's not complete. It is trying to do more experiments, trying to look for a theory that give us a prediction that we can test or look for some other data elsewhere. We are sort of at that impasse. We have a theory that works very well in terms of predicting the experiments we do in these particle accelerators. It just doesn't explain why the universe is the way it is. So it's a frustrating kind of impasse to be at. So yes, more experiments, but we probably need a better theory that will tell us a clever experiment to do rather than just building bigger and bigger accelerators and hoping that we
mashing more
something.
Atoms together and hoping for the best or the worst.
It's a very expensive way to do physics, but it's the only idea we've got at the moment.
Congratulations on your discovery, which may well prove to be among the most significant in the history of science.
I cannot accept half-baked theories that sell newspapers. I'm a scientist.
Who are you, who are so wise in the ways of science?
A most distinguished scientist, whose name we know, even in the wild of Transylvania.
Across Australia on the Community Radio Network, you are listening to Lost in Science.
Welcome back. You're listening to Lost in Science. I'm Lyndon, and I'm wondering if maybe you could just have a look at the window briefly. Just have a quick look. Look up at the sky. Can you see anything? Chris, have you got anything?
Look, the curtains are all shut here. I can't really see what's going on. I'm in my soundproof booth recording.
Oh, good. Good.
Yeah.
Did you see the sky at all today?
I have seen the sky. Yeah. And, there's all kinds of things in the sky. There's the sun, there's the moon, there are stars. But you can't always see them because sometimes there are clouds in the way.
Oh, no. Clouds. What a shame.
Yeah. Those pesky clouds. I wish we didn't have clouds sometimes.
Oh. I'll slip you that $5 for the segue later.
Yeah,
Thank you.
Yeah.
I don't wish we didn't have clouds. I'm really glad that we've got clouds, Chris.
Good.
Not
Okay.
only are they beautiful and fascinating and explain a lot about how air moves around the earth and how energy and water moves around the planet and distributes things and keeps our planet the nice habitable place that it is, but they also have a really crucial role to play in our climate. So you probably know, just like you were talking before about the various different types of quarks, there are different types of clouds. We've got 10 basic types of clouds.
Ooh.
It's hard for me to know. Do you know these?
You beat the quarks. Let me see. No, I don't think I named them all. You've got your cumulus.
Yep, good one. The fluffy ones. Cumulus, derived from the Latin, which means like heaped okay. Clouds. So they're the ones you draw if you're 4 years old and listening to the show.
Cumulonimbus?
Cumulonimbus, yes. Yep. They're the big towery ones. They go from the bottom of the atmosphere all the way up to the top, up to the troposphere, the tropopause.
Storm clouds, aren't they?
Yeah, they're the big storm clouds. They can go 10, 11 kilometres, 12 kilometres up into the atmosphere. Yep.
Cirrus?
Cirrus, well done. They're the really high icy ones. They're made of ice crystals. Cirrus derives from the Latin meaning hair, like tufts of hair.
Okay.
They're like the wispy tail ones. Yep.
Stratus.
Stratus? Oh, look at you. What am I even doing here? Yes, stratus clouds. That means that they're like the layery ones, the spread out layer ones. You get a lot of those in the UK. Your mopey day clouds, the big layered ones, derived from the Latin for layers.
And then is it mostly like combinations between like your stratocumulus and cirrostratus and those sort of things?
Yep, that's exactly right. So they've got... there's 10 main cloud types and they're divided into low, middle, and high, right? So your low clouds would be your cumulus and your stratocumulus and your stratus, yes, so they're mixed there. And then you've got your middle clouds, which are altostratus, altocumulus, and then nimbostratus. So nimbus means rain cloud in Latin. So it's a cloud, rain cloud. Nimbostratus, they often bring snow. And then up high, you've got your cirrus, your cirrostratus, your cirrocumulus, and then your big mama, your cumulonimbus cloud. And within all of those different 10 types, there's different variants as well. So different features or phenomena that some of the clouds have. So my favorite is the mammatus cloud type. I don't know if you've ever seen these.
Oh, yeah, they're kind of the bumpy ones.
Yes, they're kind of undulating. Mammata, the Latin for breast, and it's descending air underneath a storm cloud that makes those beautiful, really distinctive pockets of sinking air cloud. They're really stunning. And then there's another one that you can get with cumulus or stratus. I think it's called aspiratus, which sort of looks like waves within the cloud underneath the cloud. That's quite a new cloud name that's only been developed in the last.
They're inventing new clouds still.
Yeah,
That's great.
yeah.
Is fog a cloud, or where do we sit on fog?
Oh, well, I say that fog is a cloud. Yes, I mean cloud is when water vapor condenses and becomes water liquid that's suspended in the air, right? So I would say that that is a cloud. Whether how it fits into these 10 cloud types, I don't know.
Okay.
Local stratus, I guess. Maybe very thin stratus. Do you disagree?
No, I don't know. I'm thinking about what's the difference between fog and mist, and I don't want to go down that.
No, that's a conversation for another day. Anyway, so there's all of these different types of beautiful clouds, and they happen in different parts of the atmosphere. They happen in different parts of the world, and they bring different types of weather as well, right? Your fluffy cumulus clouds aren't likely to bring a lot of rain. Your big stratus clouds can sort of bring some misty drizzle. Cumulonimbus clouds bring big thunderstorms. Nimbostratus, lots of sort of soaking rain. But they can also do different types of reflecting of incoming solar radiation, right? So if you've got big white clouds, like the top of a big cumulonimbus cloud, for example, or say you had a lot of contrails higher up in the atmosphere from aeroplanes, those clouds are going to reflect more of the sun's energy. Yeah.
Right.
So if you have a lot of those clouds around the place, then you're going to get a lot of energy being reflected back into space. If you don't have as many of those, of course, then you're not going to get as much energy reflected back into space. You're going to get more energy coming down to hit the Earth, warming the Earth, and then that shortwave energy, like the sun's energy that comes in largely in the visible kind of spectrum, the sunlight that we see, hits the Earth, warms the Earth, and then some of that warmth is re-emitted back up into our atmosphere and trapped by different types of clouds.
Right.
This new study that's just come out recently was trying to understand the role of clouds in temperature changes that have been seen over the last few years. So I'm not sure if you remember back in the deep dark COVID days, there were some studies that were examining what happens in the atmosphere when all of our airplanes just stop, right? Mm. Everything was grounded. We had this big decrease in airplane traffic, in car traffic, in all sorts of traffic. And there were lots of studies that were done and quite a few field campaigns where a few research planes went up into the atmosphere and, measured lots of different things. And they found all sorts of stuff, particularly in Europe, actually. Some studies found that without pollution from cars, the sky actually got noticeably bluer in some areas, which was pretty cool. Without as many contrails, there was a notable, as I said, increase in absorption of shortwave radiation at the surface, which was interesting. But also, if you've got less pollution, right, if you don't have as much dust or soot or those kinds of things, then you've got fewer of what's known as cloud condensation nuclei.
Oh, okay. Yes. So things because the clouds need this kind of dust to form the droplets that make up the fluffy white stuff.
Exactly, yeah. To make a cloud, you need to have enough water vapor in the atmosphere. You need to have a change of temperature or a change in pressure that kind of makes the air cool down and makes the gaseous water, the water vapor, turn into water liquid. But then you need to have something for the water liquid to stick to. Cloud condensation nuclei. That's what they're called. And, in some parts you'll get supersaturated parts of the atmosphere, but clouds won't form because the air's too clear. It's too clean. Some parts of the Southern Ocean have that. And one of the other things that people noticed during the pandemic was when we had a big decrease in pollution, there was also a decrease in cloud cover because there wasn't as many little bits of things for the water vapor to stick to. But this study wasn't about that. This was a study that was done by, was led by a team from NASA, but it also involved a researcher from Australia as well, from Monash University. And they looked at 24 years of satellite data to try to understand how our clouds are changing in their location. So if you're trying to keep sun's energy out of the Earth to stop it from sort of increasing in its warming, right, and being trapped by greenhouse gases, you want to have these bright white clouds in the areas where you get a lot of sun, which is generally in the equator, right? If you've got lots of white clouds in the equator around in that tropical area, that's going to reflect more clouds back, energy back into space. But if you've got broken up grey clouds in that same area, then that's going to trap that sort of long wave radiation as it gets emitted back from the Earth. And these guys found that what we're seeing is a decrease in the amount of white areas of cloud, essentially, over the tropical regions. That's taken the shape of a few different things. The first is that there is a strip of storms that happens around the equator. It's called the intertropical convergence zone, right? And it's an area where we've got returning air that kind of moves towards the equator. It hits the equator. It's nice and warm there. So the air warms, rises, up it goes, up it goes. It gets cooler and cooler, forms a cloud. There's a lot of moisture around because it's very, moist environment. And you get heaps of storm clouds, right? This region, it's called the intertropical convergence zone. It moves north and south throughout the year. It's a big line of thunderstorms. If you were to look at a satellite image now, you could see it on a map. It kind of moves over us during the wet season, right? It's kind of interacts with the monsoon. It's essentially over our part of the world. It's known as the monsoon, I guess. It interacts with the monsoon. And the other thing that is moving is the band of storms that happen a little bit further away from the equator. So this intertropical convergence zone is getting narrower, more and more narrow, which means there's more cloud-free regions and there's more regions of these grey broken up clouds. And then our other areas of storm clouds that are happening further away from the equator are moving further south, right? So the bit that can't move is getting narrower, and the bits that can move are moving further away to areas that don't get as much direct sunlight because of the angle of the Earth, which means that you've got a question on your face.
I was wondering, it's happening because of warming, or is this like something else that's causing this?
No, it's happening because of warming. Right. So this is a classic example, actually, of a feedback loop in the climate system. So what we have now is a world that is a degree and a half warmer than it was 100 years ago. And because of all this extra energy, everything's getting warmer, right? So the regions that are would be considered the tropical regions in terms of their temperature profile are expanding, right? They're pushing further south. Everything's pushing further south. The temperature gradient between the equator and the poles is getting all messed up a little bit because the poles are warming faster than the equator, and everything's getting squeezed, like pushed north or south, because we've got extra greenhouse gases in the atmosphere, which also act just like those grey broken up clouds as excellent blankets for trapping the heat that comes from the Earth once it's been warmed by the sun, essentially. So this is a response to a warming planet, which is resulting in an even warmer planet. Do you know what I mean?
Gotcha. Yeah,
It's it's a feedback cycle, which is pretty nasty, but it's also fascinating to me. The two reasons why I wanted to bring this story up is that it's interesting to see these temperature records that were broken. 2024 was the hottest year on record. It beat 2023. And there were lots of theories as to why this was happening. One theory was, they've changed the ship fuel, or the ship routes have been changed, and that's led to a change in the composition of the atmosphere, which has changed the clouds in some way, shape, or form. But nobody was really quite sure. So to have these kind of big mysteries in how our Earth works is a really scary but also hopeful idea that there's still some things we don't quite know about and how how they're working and how they're interacting. But doesn't it just seem amazing that clouds have so much global power? On an individual level, you think, that's just air and water. What are you really doing?
I guess I think of them as part of the weather system, and more, I suppose, more an effect rather than a cause. But the fact that they could be a cause as well as an effect is pretty spectacular. Yeah,
you don't underestimate it. Next time you see them tomorrow, or next time you look out the window, don't underestimate those clouds. They're really doing a job, which is more powerful than you think.
Thank you. I've seen clouds on both sides now. And that's it for another episode of Lost in Science. Lost in Science is recorded for 3CR in Melbourne on the lands of the Wurundjeri people of the Kulin Nation, and it airs across Australia on the Community Radio Network with the support of the Community Broadcasting Foundation. We would love you to get in touch with us. You can email us at lostinsci@gmail.com, or you can find us on Facebook, we're Lost in Science on 3CR, or on Twitter, where we're at Lost in Science 1. You can find us on your favourite podcast app, where if you get the chance, please give us a good rating and review, as that will raise us up in the search rankings so other people can find the science. Or you can listen to us however you listen to us now, where at the same time every week, Claire, Stu and Chris get
Lost in Science!
Thanks for listening to a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online.